I think something is not clear about this plane sweep stereo, okay, which I had already explained, but just to kind of say clarify that the homography, right, that you have, what is the homography that we had for that? KL, I think what I had written was H pi P L, right? This is what I had written as a homography, as KL RL plus minus TL N transpose by dP, the whole KRF inverse, right? This is what it was. So one of the doubts was that do you actually match corresponding points and arrive at the homography, or do you kind of directly use this equation? The idea is to use this equation because there is not really a real plane out there, right? I mean, you have a 3D scene, okay, which is being watched by these cameras, right? And we are only trying to slice this guy, right, into, let's say, okay, if you take right, this to be the camera, reference camera, just slicing it into various planes at some equidistant locations, and and these planes are virtual, right? They are not real. So what you are trying to say is, if this 3D scene cuts, right, wherever it cuts, I mean, right, I'm just trying to give some sort of an approximate figure, but then, right, if you kind of look at the contour of points, right, that might cut this plane in the front. So what you are saying is that plane which is at dP, let's say, right, if this one is d1 and then you've got like d2 all the way up to whatever, right, n number of planes, and you've got m number of views. So what you are sort of saying is that for one distance d1, you can warp this reference frame using this equation, because the poses are known, right? We know R, T, the normal, as I said, is 0, 0, 1, right? That's because it's kind of fronto-parallel, right? So with respect to the reference frame, this is fronto-parallel, and KL and KR are the intrinsic matrices, and so the idea is that you kind of warp in a sort of virtual, in a virtual way, right? It's not like right, you take images from these two views and find correspondences to find the homography, because there is no single homography, by the way, right? Because this is a 3D scene, and there is no homography that will take you from this image to this image or to this image. There is no homography that can do that. If it was the case, then it would be a planar scene, right? The idea is that this is 3D, there is a translation across the cameras, and therefore, as we had said right before, that there is no homography that can bring one image and align it to the other. But here we are not talking about one homography, right? We are talking about a bunch of homographies that are coming from various depths, virtually created, and you are trying to see as to where this image, right, how this image will look if it was warped by this homography, and you are trying to compare it with this view, and the hope is that those points, right, that actually lie at that depth, which we do not know, but then there will be points that will lie, that the surface actually cuts, right, this plane, and those points are at depth d or d1, right, with respect to the first plane, and with respect to a reference camera, and therefore, right, when you actually do this warping, so those points will come, and if you try to match this warped image with this view, then it is not true that it will match everywhere, right? It will match at some points where this homography is obeyed by points that obey this homography, right? And that's how. But then, since you have multiple views, I mean, you can do it across the cameras, and as long as, and because the scene is the same, all these points are supposed to appear at their respective locations, right? And when you warp them, you should be able to compare them, and you should be able to tell whether the match is good or not for those points, and then you sort of do it for D2, then you do it for D3, and that's how you do it. Okay, so there is nothing like comparing feature points to get the homography, right? That's the way we did it in the beginning. If you remember, we said that if I have 4 point correspondences, then that gives me 8 equations, and that's all I need. But this is not like that, right? These are virtual planes. These are not real planes. These are virtual planes through which you are trying to warp, and you are trying to get a sense for this structure of the scene. Okay, so I think this is one point that I just wanted to clarify. Then today, right, what I'm going to do is I'm going to show you a few examples, okay, of which I had said last time itself that I would do. So let me just go and just show you a few examples, right? We won't spend too much time, but just to illustrate a few of the things that we have already done. Okay, so So, for example, a typical kind of a stereo head, right, looks like this. So, you have one camera here, you have another camera here. These are, so right, this is like a stereo pair, and you can actually construct your own camera if you wish, right, and you can actually take it around to capture images. And this is what we had for a parallel camera, right. So, the kind of epipolar line, we know that, right, they lie along the same line. I mean, okay, I should draw it correctly, but so for example, right, so yeah, so maybe, right, this was some other point. So, whatever it is, right. So, you have these parallel lines, and you know that the epipoles are at infinity, right. So, the E at infinity, E dash at infinity, this is a case for a non-converging or a parallel camera case, right, where it's easy to search, right. So, this is like the epipolar lines are, right, are simply the rows of the images. So, it's easy to go and search for them. When you have converging cameras, right, then your epipolar lines are no longer right, they're not in general parallel, and it's also not true that the epipoles should lie in the image. For example, in this case, you can clearly see that the epipoles are not in the image, right, they can lie outside the image. So, you can ask where is the epipole, right, in this case, and you can show that the probably epipole is somewhere outside the image, right. So, this is certainly possible. I think one of the students was asking during the, when we were actually talking about epipole, right, where they can exist and so on, and I had mentioned at the time that the epipole, right, does not have to be within the image, it can lie outside. And what you do, so you basically, right, take a coordinate from the left image, and then you act your fundamental matrix on that after you have computed f, then you find the epipolar line, and this is the line along which you have to conduct the search. And the search could be using whatever, right, you can take a small patch and then use it to compare across. That would be a traditional way of doing it, but that is still oversimplified, because in reality, right, there are issues such as variations in terms of some illumination variations could kick in, or you could have something like whatever shadows, or you could have noise, or you could have a color variation. We could have things like that happening, and therefore, right, it's not such an easy thing to just take a patch and kind of do a cross correlation. And sometimes there could be occlusions, and sometimes there could be regions of low texture where it's very difficult to match, right. Suppose you give you two, suppose right, I mean, right, think of a region like this and think of a region like that. I mean, there's really nothing unique out there, right, for me to be able to match. I mean, because when I kind of take a patch here, then maybe there is a whole bunch of things where it can match, right, on that epipolar. Of course, if it is on that row or wherever it is, right, when you match, it is not true that right, it's such an easy task, right, especially when there is regions of low texture. And therefore, right, people of course have various other ways of handling that, what are called energy minimization methods and so on, where you kind of believe that locally, right, your depth should be somewhat smooth, right, which is a reasonable assumption to make. The smoothness is something, right, that I keep telling. It's such a sort of a generic constraint, and it is so very handy, right, and just a matter of formulating it, and then usually it's a kind of a Gaussian prior that is put on the say depth map, right. Simply means that things are locally uniform, or things are locally, what do you say, they look locally similar, and which is normally true. Even in image, if you look at a pixel around it, right, things look very similar, right. And again, right, epipolar lines, you can have a situation like that, and anyway, right, I mean, so I think this is the chirality thing, but this I think I had already drawn. So, for example, right, so here is a case where the point is in the front of the camera, so right, and here is a case where the point is so in this case, yeah, so in this case, which one is it? So right, with respect to this, it's actually to the back of the camera, right, and so on. So you can see that, right, and then there could be a situation where this we discussed, right, where you can have both the point coming to the rear of both the cameras, which is not possible, right. That means you cannot image that. Then this is that similarity ambiguity, right, that we had mentioned. For example, you could have a situation where the reconstruction, right, could be up to a similarity. What that means is you can only reconstruct up to a scale factor, up to a rotation, and so on, right. So you can see that, see this kind of this one, right, I mean, this kind of reconstruction, where you can see that the ambiguity is up to similarity. I mean, you can have a projective ambiguity, right, which basically means that something like this could look like something like this, and yet that is also equally valid, right. I mean, you cannot complain, I mean, because that's the ambiguity that you have in the problem fundamentally. The previous one, what it is saying is that, for example, right, I mean, if you had an original structure like this or whatever was the original structure, then all these are sort of equivalent reconstructions. I mean, you could have you could have a rotation of this, right, which is what this is. You could have a scaling; it may look smaller. So a similarity is like what you can have scale, translation, and this rotation, right? So all three ambiguities could be there, and still it's okay. It's perfectly okay. I mean that is the level of ambiguity that is kind of right inherent in the problem, and therefore all these are okay. I mean, and so we don't have a problem, and we accept all these solutions. Then the multi-baseline stereo results, right, typically would look like this. I mean, if you were to do this kind of a plane sweep stereo, right? This one, right? This is that plane sweep stereo, right? So what this means is that so by left neighbor, right, what they mean is you have taken a reference image to be somewhere in the middle. I mean, I kept taking one out of the left, but you can take in the middle, that to be the reference, and then you can check what's happening to the images on the right when you warp them, what happens to the images on the left when you actually warp them, or you take the reference and warp, whichever way. In one case, it's just the inverse of the original homography, right? So if you do that, so what really happens is, so for example, right, when you actually warp, right, with respect to various so you see this kind of right, a blurring effect, right? So what this really means is that that's what it means. So you cannot align images through a simple homography because it's actually a 3D scene, right? So when you actually bring them up, so surely, right, there are points here which I think you are not able to immediately spot, but there are points where the overlap is perfect, and there are points where it is not. That means right, when you kind of look at it, it looks like something is blurred out, right? And that's because they are not being aligned, and they cannot get aligned. If it's a 3D scene, right, they cannot get aligned. It's not possible to align them. That's a fundamental thing which we know. Using a single homography, you cannot align them, right? Therefore, if you actually bring these guys together, you will find that only some points which are lying at that depth will match across views, right? And that is what you in fact use. One simple way is to sort of look at this whole volume, right, which is called a kind of a cost volume. Right, it's called a kind of a cost volume. That means you warp and then right, you kind of build a volume, and through this, right, you try to kind of measure what kind of similarity you have. So for example, one way to look at it is if I compute the variance, right, along the frames, then wherever I get a low variance, that means that those guys are all okay. That means that this is like one volume is for one depth. All views warped with respect to one depth will be like one volume, right? You guys follow that, right? I'm just saying I have these different views. I choose one depth and I warp, right, all of them. Then what will you get? I mean, you'll get a stack of frames, right? Now, if you look at the stack of frames, they won't be aligned because it's not like all points are going to get aligned. But there will be points, right, in this volume wherein if you compute the variance along the stack, then what will you find? You will find that there are certain points that were lying at that depth of the plane. So whichever view you take, because your R and T and all are already estimated, so what it will mean is it will all align up. They will kind of line up, right, in right, I mean, in that place, because this is after the warping. Right? This is not a reference view, right? This is a reference view warped, right? And when you kind of say compare it with the image that you already have, you will find that right, that there are these pixels, right, that are actually aligned, right? And therefore, for them the variance is going to be very low. Whereas for the other pixels that are not aligning, right, you will have a variance, right, which will show up to be high because they don't get aligned. And therefore, right, using that you can tell as to what value to assign, right, to that particular this one, the pixel location. So you know that this pixel is at depth C D1 and so on, right? And maybe for another plane, right, another set of points will come and then they will line up, and therefore you will get different depth and so on. This is again I think another case of the same thing. Okay. Yeah, I just thought I'll just show you these examples just because I've been telling that I'll show, but